This is the lecture for section 4.4, Polynomial Functions, Roots, and Reducibility. We'll start by talking about polynomial functions. So far, we've been working with polynomials in a formal sense, where the x that appears in a polynomial f of x serves as a placeholder to help us keep track of the coefficients. However, we can also view polynomials as functions. As we'll see, this will provide us additional tools for testing polynomials for irreducibility. We'll assume throughout this section that R is a commutative ring. Suppose f of x equal a sub n x to the n plus down to a sub 2 x squared plus a1x plus a0 is a polynomial in the polynomial ring R bracket x. Then f of x induces a function f from the ring R to itself defined by f of r equal a sub n r to the n plus down to a sub 2 r squared plus a1r plus a0 for each element r in R. This function is called a polynomial function. Now note the distinction between the polynomial f of x and the polynomial function f of r. In the polynomial f of x, the letter x is an indeterminate in the ring R bracket x. In the polynomial function f of r, the letter r is a variable which can be replaced by an element r in the ring R. Often, however, the letter x is used for both the indeterminate in the polynomial and the variable in the function, in which case the meaning has to be determined from the context. For our first example, consider the polynomials f of x equal x to the fourth plus x plus 1 and g of x equal x cubed plus x squared plus 1 in Z3 bracket x. We want to show that f and g induce the same function on Z3. Now the polynomial f of x induces the function f from Z3 to itself, defined by f of r equal r to the fourth plus r plus 1 for each r in Z3. Then f of 0 will be 0 to the fourth plus 0 plus 1, which is 1. F of 1 is 1 to the fourth plus 1, which is 3, which is 0 in Z3. And f of 2 is 2 to the fourth plus 2 plus 1, which is 1 in Z3. The polynomial g of x induces the function g from Z3 to itself, defined by g of r equal r cubed plus r squared plus 1 for each element r in Z3. Then g of 0 will be 0 cubed plus 0 squared plus 1, which is 1. G of 1 is 1 cubed plus 1 squared plus 1, which is 0. And g of 2 is 2 cubed plus 2 squared plus 1, which also equals 1. Comparing values, we see that f of r is equal to g of r for all elements r in Z3, which means that f of x and g of x induce the same function on Z3, even though f of x and g of x are different polynomials in the polynomial ring Z3 bracket x. Next, we want to talk about roots of polynomials. We can use roots of polynomials to investigate irreducibility. For our definition, let R be a commutative ring and let f of x be a polynomial in R bracket x. And element a of R is a root or 0 of the polynomial f of x, provided that f of a is equal to 0 sub r. That is, the induced function f from R to itself maps a to 0 sub r. For an example, we can ask what are the roots of f of x equal x squared plus 1 in the real numbers r, or in the complex number c. Well, in R, we know that there are no solutions to the equation x squared plus 1 equals 0. So the polynomial f of x equal x squared plus 1 has no roots in the real number field R. In C, however, f of negative I is equal to 0, and f of I is also 0. So both negative I and I are roots of f of x in the complex number field C. So this illustrates that the roots of a polynomial depend not only upon the formula for the polynomial function, but also for the field that we're looking at. For our next example, we want to find the roots of f of x equal x squared minus 1 in Z8. Testing each element of Z8, we obtain f of 0 is 0 squared minus 1, which is 7. F of 1 is 1 squared minus 1, which is 0. F of 2 is 2 squared minus 1, which is 3. F of 3 is 3 squared minus 1, which is 0. F of 4 is 4 squared minus 1, which is 15, which is equal to 7 in Z8. F of 5 is 5 squared minus 1, which is 24, which is 0. F of 6 is 6 squared minus 1, which is 35, which is 3 in Z sub 8. And finally, f of 7 is 7 squared minus 1, which is 48, which is equal to 0 in Z8. So this shows that 1, 3, and 5, 1, 3, 5, and 7 are all mapped to 0 by the polynomial, by the function induced by the polynomial. And therefore, f of x has roots 1, 3, 5, and 7. Now, to investigate the connection between the roots of a polynomial and its irreducibility, we're going to restrict our focus to polynomial rings over a field. It turns out that if we consider just polynomial rings over a field, we're able to say much more than if we just try to look at arbitrary commutative rings. For our first theorem, theorem 415, we have the remainder theorem. Let f be a field, f of x be a polynomial in f bracket x, and a be an element of f. The remainder, when f of x is divided by x minus a, is f of a. To prove this, we're going to apply the division algorithm, and when we divide f of x by x minus a, the algorithm tells us there exists a quotient q of x and a remainder r of x, for which f of x is x minus a times q of x plus r of x, and the remainder is either 0 or the degree of r of x is less than the degree of x minus a. Since there are two possible results for the remainder, we have two cases. In both cases, we want to show that the remainder r of x equals f of a. So case 1, we'll suppose that our remainder r of x is 0. Then f of x is just x minus a times q of x, so that f of a will be a minus a times q of a, and a minus a is 0, so 0 times q of a will be 0, and that's equal to our remainder. So this proves that f of a is equal to r of x, which proves case 1. In case 2, we'll suppose that the degree of r of x is strictly less than the degree of x minus a. Since the degree of x minus a is 1, this implies that the degree of r of x must be 0. So r of x is a non-zero constant polynomial. Substituting a into the formula for f again, we obtain f of a is a minus a, q of a, plus r of a, and the first term is 0, and we're left with just r of a. And since r of x is a constant polynomial in this case, then r of x must equal r of a, which equals f of a. So again, this shows that r of x, our remainder, is equal to f of a, and this proves case 2, which completes the proof of the theorem. As an example of how we can apply the theorem, we can find the remainder when the polynomial f of x equal 3x to the 4th plus 2x cubed plus 6x plus 4 is divided by x minus 5 in Z8 at bracket x. In order to apply the theorem, let's first rewrite the divisor x plus 5 as x plus minus 3, which is x minus 3. According to the theorem, the remainder is then f of 3, which will be 3 times 3 to the 4th plus 2 times 3 cubed plus 6 times 3 plus 4. And 3 to the 4th is 81, which is 1 in Z8. 3 cubed is 27, which is 3 in Z8. So we obtain 3 times 1 plus 2 times 3 plus 2 plus 4. So that's 9 plus 6 is 15, which in Z8 is 7. So f of 3 is 7, and that's our remainder when the polynomial is divided by x plus 5. For our second theorem, theorem 416, this is called the factor theorem. Let f be a field, f of x be a polynomial in f bracket x, and a be an element of f, then a is a root of the polynomial f of x if and only if x minus a is a factor of f of x in f bracket x. This is one of our standard results from college algebra or even intermediate algebra, where if we know that an element or number is a root, then we obtain a linear factor of the polynomial. Well, this is the biconditional, so we have our two directions. First, our forward direction. We'll suppose that a is a root of f of x. We need to show that x minus a is a factor of f of x. Applying the division algorithm, again dividing f of x by x minus a, there exists a quotient q of x and a remainder r of x such that f of x is x minus a times q of x plus r of x. And by the remainder theorem, the remainder is r of x is f of a. And since a is a root of f of x, then r of x is equal to f of a, which is equal to 0. So f of x is x minus a times q of x. Therefore, x minus a is a factor of f of x. And this proves the forward direction. For the backward direction, we'll suppose that x minus a is a factor of f of x. We then need to show that a is a root. Since x minus a is a factor of f of x, this implies f of x is x minus a times g of x for some g of x in f bracket x. Then f of a is a minus a times g of a, which is 0 times g of a, which is just 0, which implies that a is a root of f of x, and this proves the backward direction. For an example of applying this theorem, we can use it to show that f of x equal x to the fifth plus 2x to the fourth plus 3x cubed plus 4x squared plus 5x plus 6 is reducible in Z7 bracket x. Now, if we can show that f of x has a root a in Z7, then it follows from the factor theorem that x minus a is a factor, and then f of x will be reducible. Now, since x minus 1 is a factor, and therefore f of x is reducible in Z7 bracket x. Now we're going to have a series of several corollaries of the factor theorem. For the first corollary, 4.17, let f be a field and f of x a non-zero polynomial of degree n in f bracket x. Then f of x has at most n roots in f. So the degree of a polynomial gives us an upper bound to the number of roots in our field. To prove this, we're going to use mathematical induction. We want to prove for all n greater than or equal to 0 p of n, where p of n is the propositional function for all non-zero polynomials f of x in f bracket x of degree n, f of x has at most n roots in f. For the basis step, we need to show p of 0 for all non-zero polynomials f of x of degree 0, f of x has at most 0 roots in f. Now, a non-zero polynomial of degree 0 is a non-zero constant polynomial, which has 0 roots. Therefore, p of 0 is certainly true, which proves the basis step. For the induction step, we need to show for all k greater than or equal to 0, p of k implies p of k plus 1. So we'll suppose k greater than or equal to 0 is arbitrary. Suppose p of k is true. We then need to show p of k plus 1 for all non-zero polynomials f of x in f bracket x of degree k plus 1, f of x has at most k plus 1 roots in f. So let's suppose that f of x in f bracket x is an arbitrary non-zero polynomial with degree k plus 1. We need to show that f of x has at most k plus 1 roots in f. Consider the following cases. Case 1, suppose f of x has no roots in f. Then the result clearly holds. For case 2, we'll suppose f of x has at least one root in f. Now keep in mind, when you do a proof involving cases, your cases have to be exhaustive. So they have to include all possibilities. So you can see that our two cases here, case 1 was suppose f of x has no roots, case 2, suppose f of x has at least one root, exhaust all possibilities. So let's suppose that a is a root of f of x in f. By the factor theorem, x minus a is a factor, so that f of x is x minus a times g of x for some g of x in f bracket x. Then the degree of f of x will be the sum of the degrees of the two factors, so it will be the degree of x minus a plus the degree of g of x. And since the degree of f of x is k plus 1, and the degree of x minus a is obviously 1, this implies that the degree of g of x must be k. Now since f of x is non-zero, then so is g of x. Since g of x being 0 would imply that f of x is 0. The induction hypothesis then implies that g of x has at most k roots in f. Now note that for any root b in f of x, b not equal to a, f of b will be b minus a times g of b, which is 0 since b is a root of f of x, which implies that g of b is 0, so that b is a root of g of x. So the roots other than a of f of x must be roots of g of x. Now since g of x has at most k roots in f, it then follows that f of x has at most k plus 1 roots in f, the at most k roots of g of x together with the root a. And this proves p of k plus 1, which proves case 2, which proves our induction step. And this completes the proof of the corollary. Now, in an example earlier in this section, we showed that the polynomial f of x equal x squared minus 1 had 4 roots in Z8. Now, since Z8 is not a field, the corollary doesn't apply. But as this example illustrates, polynomials can behave very differently in rings which are not fields. For our next corollary, 4.18, let f be a field and f of x be a polynomial in f bracket x with degree of f of x greater than or equal to 2. If f of x is irreducible in f bracket x, then f of x has no roots in f. To prove this, we'll suppose f of x is irreducible in f bracket x. We need to show that f of x has no roots in f. Now since f of x is irreducible in f bracket x, then by theorem 4.11, f of x cannot be written as the product of two polynomials of lower degree. Since the degree of f of x is greater than or equal to 2, this means that f of x has no linear factors of the form x minus a in f bracket x, which implies by the factor theorem that f of x has no roots in f. And so this proves this corollary. Now, an important remark is that the converse of corollary 4.18 is false in general. That is, if f of x has no roots in f, it does not follow that f of x is irreducible in f bracket x. For example, consider the polynomial f of x equal x to the fourth minus 4 in q bracket x, where q is the field of rational numbers. Then f of x is reducible in q bracket x since it factors using the difference of two squares factorization as x squared minus 2 times x squared plus 2. However, f of x has no roots in q. The only roots of f of x will be plus or minus square root of 2 and plus or minus I square root of 2, none of which are rational. So now while the converse of corollary 4.18 is false in general, it is true in the case that f of x has degree either 2 or 3. And this is the result of our next corollary. So corollary 4.19, let f be a field and let f of x be a polynomial in f bracket x of degree 2 or 3. Then f of x is irreducible in f bracket x if and only if f of x has no roots in f. So this is a biconditional, so again we have both directions, and the forward direction follows immediately from corollary 4.18. It's just a special case of corollary 4.18. To prove the backward direction, we need to show that if f of x has no roots in f, then f of x is irreducible in f bracket x. We'll use a proof by contrapositive. We then want to prove the contrapositive statement, which is if f of x is reducible in f bracket x, then f of x has a root in f. So suppose f of x is reducible in f bracket x. We then need to show that f of x has at least one root in f. Since f of x is reducible in f bracket x, then theorem 411 implies that f of x can be written as the product of two polynomials of lower degree. That is, there exist polynomials g of x, h of x in f bracket x, such that f of x is equal to g of x times h of x, and the degree of g of x, the degree of h of x, are both strictly less than the degree of f of x. By theorem 4.2, the degree of f of x is the sum of the degrees of g of x and h of x. And since the degree of f of x equals either 2 or 3, and the degree of g of x and the degree of h of x are both strictly less than the degree of f of x, then one of these factors must have degree 1. In the case that the degree of f of x is 2, they will both have degree 1. In the case that the degree of f of x equals 3, then one must have degree 1 and the other degree 2. Suppose without loss of generality that the degree of g of x is 1. Then g of x will be a linear polynomial, so g of x will look like cx plus d for some elements c and d in f, where c is not equal to 0. Now since f is a field and c is not equal to 0, then c inverse exists in f. And g of x can be rewritten as c times the quantity x plus d c inverse, which is c times the quantity x minus a minus dc inverse. It then follows that minus dc inverse in f is a root of g of x, so must be a root of f of x in f. And this proves the backward direction. As an example of how we can apply the theorem, we can show that f of x equal x cubed plus x plus 1 is irreducible in Z5 bracket x. And we can test each of the elements in Z5 to see if f of x has any roots. So f of 0 is 0 cubed plus 0 plus 1, which is 1. F of 1 is 1 cubed plus 1 plus 1, which is 3. F of 2 is 2 cubed plus 2 plus 1, which is 11, which is equal to 1 in Z5. F of 3 is 3 cubed plus 3 plus 1, which is 31, which is 1 in Z5. And finally, f of 4 is 4 cubed plus 4 plus 1, which is 64 plus 5 is 69, which is 4 in Z5. So this shows that f of x has no roots in Z5, and since the degree of f of x is 3, then corollary 419 tells us that f of x is irreducible in Z5 bracket x. For our next corollary, 420, let f be an infinite field and f of x and g of x be polynomials in f bracket x. Then f of x and g of x induce the same function from f to itself if and only if f of x is equal to g of x in f bracket x. So this is saying that the functions induced by the polynomials f of x and g of x are the same function if and only if the two polynomials are equal in the polynomial ring. So we've got two directions again. So for the backward direction, we'll suppose that f of x is equal to g of x in the polynomial ring f bracket x. Then it's clear that the two functions will be the same, so that f of r is equal to g of r for each r in f. Since the polynomials are equal, all the coefficients in the polynomials are equal, and so then the two functions are identical. So f of x and g of x induce the same function from f to f. For the forward direction, we'll use a proof by contradiction. So we'll suppose that f of x and g of x induce the same function from f to f, but f of x is not equal to g of x in f bracket x. So the functions are the same, but the two polynomials are not. we then need to derive a contradiction. Since f of x is not equal to g of x, then the polynomial h of x, which is the difference of the two, f of x minus g of x, is not the zero polynomial. Since f of x and g of x induce the same function from f to f, however, then f of a equals g of a for every element a in f, and this implies that h of a equal f of a minus g of a is 0 for every a in f, which means that every element a in f is a root of the polynomial h of x. So h of x is not the zero polynomial, but every element of our field is a root of the polynomial. Now we're supposing that f is an infinite field, and since f is infinite, this means that h of x has infinitely many roots. However, corollary 4.17 implies that h of x has at most the degree of h of x roots. And this is a contradiction, and therefore the forward direction holds. Now, in the example at the beginning of this section, we showed that the two polynomials, f of x equal x to the fourth plus x plus 1, and g of x equal x cubed plus x squared plus 1, induce the same function on Z3, even though f of x is not equal to g of x in Z3 bracket x. Corollary 4.20 shows that this cannot occur in the case of an infinite field, but in this particular example, our field was obviously finite, Z3.